There are even more problems with simply sorting objects and drawing them roughly back to front. For example, notice that the back faces are not shown for any transparent objects. If you turn back faces on, you'll start to get strange rendering artifacts. Some back faces will be drawn before front faces blend with them, some won't, giving this patchy look. For example, here's a view of a block from the side, along with an order that the faces are drawn. Since face 1 is drawn first, face 2 blends with it. Face 3 is drawn, filling the Z buffer, and also blends with face 1. Face 4 is behind face 3, so is invisible when rendered. Of the two back faces, in this case only face 1 has had an effect on the image generated. Even with back face culling on and a good sort order, you can still have problems with different sized objects. Say a ground plane and a red object resting on it are both transparent. The middle of the ground plane is closer to the camera, so by sort order it will be drawn after the red object. This will make the ground plane to appear to be above the red object. Here's one more problem with transparency. Complex objects can have two or more surfaces overlapping a single pixel. Again, it depends on draw order as to what appears on the screen. If the fragment on the left is drawn first, then the fragment on the right will improperly blend with it at this pixel. There's even research about the ordering of triangles in the mesh itself to avoid these problems, but this type of technique can be costly to apply. At this point, you might have given up all hope for transparency always working right. The Z buffer was meant to store only one object at a time, and unless you can guarantee the order of objects covering the pixels, there's little else you can do. There are some further tricks you can do by only reading and not writing to the Z buffer, but there's no perfect solution. If you desperately want to get the right answer, there is one technique that works fairly well called depth peeling. The idea is to peel away each transparent layer until all layers are processed, by storing an additional minimum Z depth for each pixel. So, for example, the first layer is all the transparent surfaces closest to the camera. The second layer is all the second closest surfaces. The third and fourth layers are processed in turn until the whole object is rendered. That's conceptually the key idea. See the additional course materials for more about this algorithm. The drawback is that each peel operation needs to have all the transparent objects rendered again. Many passes may be needed before all the layers are found and processed. Ultimately, what would solve the transparency problem is storing a list of all the transparent fragments in each pixel, along with their depths. This approach is known as the A buffer. Once we have all this information, we can then combine these fragments in the right order. This type of storage is possible in newer GPUs for the desktop, but can use a considerable amount of memory. What's interesting is that mobile devices usually use a different architecture, called tile-based, that can more easily keep such fragment lists around. Yet another approach is called Stochastic Transparency, which uses screen door transparency within the pixel itself along with some randomness to get a reasonable average result. This brings us full circle back to the original transparency algorithm I presented. There's no simple answer on the GPU.